Your database is crawling, and at a million rows, a linear scan is a death sentence for your latency. To go from O of n sluggishness to millisecond logarithmic lookups, you need to master one data structure, the B tree. Today we're dissecting how these multi-level structures stay perfectly balanced, even while millions of writes are hammering them. By the end of this video, you'll know exactly why your index is fast, exactly what it costs you, and exactly when it silently stops working. Let's make this concrete. We're building the feed for something Instagram shaped. One table posts 10 million rows, and the single most common query in the entire product is this: give me the last 20 posts by this user. That's it. That's the whole query. Now here's what the database does if there's no index on that table. It starts at the first row, checks, is user ID 8842? No. Next row, no. Next row, no. It does that 10 million times. This is a sequential scan, and the cost grows linearly with your table. That's your O of n. 842 milliseconds. And look at that second to last line. Rows removed by filter. 9,999,979. We read 10 million rows to return 20. And I want to be precise here, because this is where a lot of explanations oversell it. 842 milliseconds for one query on its own is survivable. That's not what kills you. What kills you is that this query runs 50,000 times a second. Every one of those scans drags the entire 200 megabyte table through your buffer pool, evicting everything actually worth caching. Your disk saturates, latency goes vertical, and it doesn't degrade gracefully. It falls off a cliff the day your table outgrows RAM. So we need a different access path, and the obvious first idea is the wrong one. Every one of us learned the answer to make search fast in a data structures class. Binary search tree. Sort the keys, and at every node you throw away half the remaining data. 10 million rows, log base 2. That's about 24 hops. 24 beats 10 million. Ship it. Except in a real database, this is catastrophically slow. And understanding exactly why is the entire insight behind B+Trees. Here's the thing your algorithms class quietly assumed, that every node access costs the same. In memory, roughly true. Reading a random address from RAM takes about 100 nanoseconds. Your index does not live in RAM. It lives on disk because it's bigger than RAM. And a random read from an SSD is about 1,000 times slower than RAM. From a spinning disk, 100,000 times slower. So look at what our beautiful binary tree actually is. It's a pointer chase. Every hop lands on a different node in a different place on disk, and every hop is a fresh random read. 24 hops, 24 random reads. On NVMe, that's about 2.5 milliseconds. Which, again, being honest, sounds fine. Until you're running 50,000 of these a second and every single one is a random, I/O your disk queue has to service. Now you're not latency bound, you're IOPS bound, and you've hit a hard ceiling. The binary tree optimized the wrong number. It minimized comparisons. Comparisons are free. What we actually have to minimize is disk reads. Here's the fact that changes everything. Disks don't read bytes. They read pages, fixed size blocks. Postgres uses 8 kilobytes. MySQL's InnoDB uses 16. And this is the part people miss. Reading 1 byte of disk and reading the whole 8 kilobyte page cost you essentially the same. Same seek, same round trip. The transfer is basically free. The trip is what's expensive. So our binary tree is doing something genuinely absurd. It pays for an entire 8 kilobyte page load and then uses about 16 bytes of it. One key, two child pointers, the other 99.8% of what we just paid for gets thrown away. That's the whole realization. If a page is what we pay for, a page is what a node should be. So we stop building nodes with two children. We build one node that fills the entire page. Pack in as many keys as fit. Let's do the arithmetic. 8 kilobytes. 8192 bytes. We're indexing a big int, which is 8 bytes. Add the pointer to the child node or the row, plus per entry overhead. Call it 20 bytes per entry all in. Roughly 400 keys in a single node. 400 children per node instead of 2. That number, how many children one node can have, is called the fanout. And fanout is the entire ball game. Let's count what a fanout of 400 actually buys us. Level 0. One node, the root. 400 keys, so it points to 400 children. Level 1. 400 nodes. Each holds 400 more keys. 400 times 400. That's 160,000 children. Level 2. 160,000 nodes, 400 entries each. 64 million rows. 3 levels. That's our 10 million row table with room to grow 6 times over. And any row in it is 3 hops from the root. Not 24. 3. Add a fourth level and you're addressing 25 billion rows in 4 hops. This is what people mean by logarithmic, and it's why the base of that logarithm is the thing that actually matters. Log base 2 of 64 million is 26. Log base 400 of 64 million is 3. Same big O. 9 times fewer disk trips. But it gets better than that, and this is the part that makes B+Trees genuinely beautiful. Count the memory for the top 2 levels. 1 root plus 400 nodes. 401 pages. 8 kilobytes each. That's 3.2 megabytes. Your entire navigation structure, everything above the leaves, fits in 3 megabytes of RAM. It's permanently cached. It never leaves. So when a real query comes in, hop 1, memory. Hop 2, memory. Hop 3, the leaf. That's your one disk read. 1. Compare that to the binary tree, where even if you cache the top 10 levels, you've still got 14 random reads left to go. High fanout doesn't just shorten the path, it makes the path cacheable. Now, small correction to everything I've drawn so far. Because what Postgres, MySQL, SQL Server and Oracle actually ship isn't a textbook B tree. It's a B+Tree. And the difference is a design decision worth understanding. In a B+Tree, internal nodes hold no data. None. They're pure signposts. Keys and child pointers, nothing else. All of the actual row pointers live in the leaf level. 2 consequences, and both of them matter enormously. 1. Because internal nodes carry no payload, they're pure navigation. So you cram even more keys per page, fanout goes up and the tree gets shorter still. That 3.2 megabyte cached upper level, that's a B+Tree property. 2. And this is the good one. Every leaf node is linked to its neighbors. A doubly linked list running along the bottom of the tree in sorted order. Think about what that unlocks. Where created at is between March and April. You traverse from the root down to the first matching leaf. 3 hops, and then you just walk sideways. No going back up, no retraversing. Sequential reads along a linked list, which is the one thing disks are genuinely fast at. And now go back to our original query. Index on user ID and created at, which means the leaf level is sorted by user and within each user by time. So, last 20 posts by user 8842 becomes 3 hops down to where that user's entries begin. Then read 20 entries sideways. Stop. No sort step, no scan. The order by is free because the data was already stored in that order. 842 milliseconds to 0.094. Roughly 9,000 times faster. Same hardware, same query, same data. Everything so far assumed a static tree. Real tables take writes constantly. So how does this thing stay balanced when a million inserts a minute are landing in random places? Because balanced isn't a nice to have here. If one branch of the tree grows deeper than the others, queries hitting that branch cost more disk reads. Your P99 latency quietly rots. The guarantee only holds if the tree is perfectly balanced. And B-trees hold that guarantee absolutely. Every leaf is always at exactly the same depth. Always. Here's the mechanism. I'll use a fanout of 4 instead of 400 so it fits on the board. Insert 25. Traverse down, find the right leaf. There's a free slot. Drop it in, keep it sorted, done. Now insert 27. The leaf is full, and this is where the magic happens. The node splits. Take the 5 keys, cut them down the middle. Left node gets 10 and 20. Right node gets 27 and 30. And the middle key, 25, does not stay at the leaf level. It gets promoted into the parent, where it becomes the signpost, separating the two new children. Less than 25, go left. 25 or more, go right. Now, what if the parent is also full? Same thing. It splits and its median gets promoted up to its parent. The split cascades upward, and in the worst case, it reaches the root. When the root splits, a new root is created above it, and the tree gains a level. And this is the whole trick, so let me say it plainly. B-trees grow up, not down. A binary search tree grows downward. You hang a new node off a leaf, and that branch gets deeper while the others don't. That's how it degenerates into a linked list, and how your O of log n quietly becomes O of n. A B-tree can only ever get deeper by adding a level at the root, which means every leaf drops by exactly 1, simultaneously. Balance isn't something the tree repairs after the fact. It's structurally impossible to violate. There's a second invariant riding along. Every node except the root must stay at least half full. Deletes that drop a node below the threshold, trigger a merge with a sibling. A split running in reverse. That's what stops the tree from becoming a sparse, mostly empty structure, where you're paying for page reads that return almost nothing. Balanced depth, guaranteed occupancy. Those two invariants together are what let a database promise you. Millisecond lookups on day 1 and on day 1000. None of this is free, and this is the half of the conversation that separates people who've read about indexes from people who've run them in production. 1. Storage. An index is a whole separate structure on disk. A B-tree on a single bigint column over 10 million rows runs roughly 210 megabytes, commonly 20 to 30% of the table itself. Put 5 indexes on a table and your index data can outweigh your actual data. 2. Write amplification. This is the big one. Every index is a copy of your data that has to stay correct. So a single insert on a table with 5 indexes isn't one write. It's the heap write, plus 5 B-tree traversals, plus 5 leaf modifications, plus write ahead log entries for all of it. And if any of those leaves is full, you pay for a split too. Indexes make reads faster by making every write slower. That's the trade, and it's not optional. 3. And this one bites people in production. Your primary key choice. If your primary key is a random UUID version 4, every insert lands at a random position in the leaf level, which means the page you need is almost never in cache. Read it, dirty it, write it back. Do that for every insert, and your write working set becomes the entire leaf level of the index. With a sequential key, auto increment UUID version 7, every insert goes to the rightmost leaf. Same page every time, permanently hot in memory. Databases even special case it. Postgres and InnoDB both optimize right edge splits to pack those pages nearly full, where random splits leave pages about half empty. Same schema, same row count. Random UUIDs give you an index that's meaningfully larger, more fragmented, and slower to write into. If you need UUIDs, use version 7. Same uniqueness properties, time ordered prefix, and your B-tree behaves. 4. Low cardinality kills indexes. Index a boolean where 95% of rows are false, then query for false. The planner looks at it and does a sequential scan anyway. Correctly. Fetching 9.5 million rows through an index means 9.5 million random heap lookups, which is far worse than reading the table straight through. Rough rule. Once a query returns more than 5 to 10% of the table, sequential wins. An index on a low selectivity column is pure write overhead and zero read benefit. 5. Column order in composite indexes. Our index was user ID, then created at. A composite index is sorted lexicographically, so it can serve a query on user ID or on user ID and created at. But it is nearly useless for a query on created at alone. It's a phone book sorted by last name then first name. Find everyone named Sharma? Instant. Find everyone whose first name is Dhruva? You're reading the entire book. This is the leftmost prefix rule, and it's why I added an index and nothing got faster is usually a column order problem. And one bonus win, covering indexes. If your index contains every column the query asks for, the database never touches the table at all. It answers straight out of the leaf. Postgres calls it an index-only scan. Trades a bit more index size for eliminating an entire disk hop. So, the mental model to walk away with. A B-tree is not a fast search tree. It's a search tree that was redesigned around the cost of a disk read. Wide instead of deep, so the navigation layer fits in memory and only the final hop touches storage. It's the reason a query across 100 million rows finishes before you can notice it happened. And one last thing worth knowing, because it's a system design interview favorite. B-trees are red optimized. They update in place, which costs you random writes. That's why write heavy systems, Cassandra, RocksDB, most modern time series stores, reach for LSM trees instead. Buffer writes in memory, flush sequentially, merge in the background. Faster writes, more complex reads. There's no universally correct index. There's only which side of that trade your workload lives on. If you want the LSM tree deep dive, say so in the comments. That's the natural sequel to this one. Go run explain analyze on your slowest query today. Look for sexcan. That's your homework. I'm Dhruva, this is the Tech Intern. See you in the next one.